Hello everyone. This is the ultimate problem session 12 of the hot track of the HoTTEST summer school. Today we'll be doing a little bit of Univalent combinatorics and trying to get a sense of sort of binomial formulas and trying to work more with finite sets again. Similarly to some of the previous sessions, not all of the problems will be covered here. So in case you're seeing this on YouTube, you should also look at the other problem session in the North American time. So you can, for example, look at the solution of problem 5. So with this said, let's get started. So recall, I wanted to, just in case you recall, that sort of we have this classical n choose k formula, which gives you n factorial over k factorial n minus k factorial. And this is exactly the formula that we sort of want to do internally in homotopy type theory. And it turns out that univalence really helps us with that. And this is exactly the behavior that we want to simulate. And it's exactly the intuition we want to have moving forward, solving a lot of these problems. So one lemma that I want to recall beforehand is lemma 17, if I'm not mistaken, 5.8, which says that let A be types, then we have the following equivalence, that taking a coproduct with the unit, and then applying the choice, we have the following equivalence. Again, very much piggybacking on the intuition we get from usual combinatorics. So with that said, we'll do problem 1. Part A says to count the elements of, and I put this in quotation simply because there is, of course, a formal way of saying this. Then finite set 3 elements, finite set 2 elements. So, okay, so using the intuition we get from combinatorics, I want to say that this is actually equivalent to fin 3, right? And so what's the way of making this precise? Well, proof is sort of follows by the formula I described above, right? So we basically just are building up our choice. So it's 3 and 2, which is by definition the same as fin 2 coproduct with 1 and fin 1 coproduct with 1, and then taking coproduct with the choice of finite set on no. So this followed from the definition, and now we can use the lemma. So the lemma tells us what? The lemma tells us that it's the same as doing a choice on a finite set on 2 elements, finite set on 1 elements, then taking the coproduct with finite set on 2 elements and finite set on 1 element, again, plus 1. So, and again, we can use the lemma, and now to sort of save time, we will not be unfolding the definitions, but this is going to be the same as choosing from finite sets of 1 element, finite set 0 elements, plus finite set on one element, finite set on one element, plus finite set on two elements and finite set on two elements. So, okay. And we know what? Well, we know that this is, right, the same as, well, I should say this should be more equivalent to choosing 0, 1, right? And then we have following elements. Okay. So this by the lemma we know is equivalent to the unit. And the kind of conjecture they want to make, again, piggybacking our intuitions from combinatorics, is that these two terms are also going to be equal to the unit. And so, well, we can unfold further these equivalences using the lemma, or we can prove sort of the usual lemma ones want to prove in this combinatorial setting, is that when we take finite set on elements and we try to make the same ones, this is going to be equivalent to the unit. All right, and the way that I'll be doing this specifically for finite sets is that because it will actually lead us to the solution of part C of our problem. And this is a nice general lemma to have. So proof of lemma, proceed by induction on n. Okay. Base case when n is 0. Well, we know then that is going to be definitionally just this choice. However, we know by the lemma that this is exactly equivalent to 1. So we're done. So inductive step. We wanna, what will we have? We have that when n is some k plus 1. Let's do it this way. Let's find k. We're already unfolding definitionally what the definition of finite sets on k plus 1 elements is. Then we apply the lemma, and we get that this is the same as finite set of k elements from finite set of k elements using finite sets of k elements, right? So, and we know what this is by the inductive hypothesis. And here we have a finite set on k elements and finite set on k elements, a product with the unit. So by the inductive hypothesis, this is the unit. And the conjecture here is that, of course, it should be empty. And how so? So claim. So this type K1 or general K is empty. So recall that this is sigma x in BS k plus 1 x decidable embeddings into A. Okay, so basically, what are we trying to say is that assuming we get an element of this type, we get an element of the empty type. Also, suppose we have such an X with an embedding. X is equivalent by the definition of this BS is equivalent to finite says on k+1 elements. Okay, so instead suppose suppose that we have an embedding of this form into and set on k elements. Okay, so by universal property of coproducts, this comes from two functions, f from fin k to fin k, and g from the unit to fin k. So, and for our original function, to be an embedding, its individual components ought to be, and specifically, its individual components should not be in any way intersecting. So, in particular, for their as G is an embedding. And this follows from one of the exercises in the worksheets that we've done previously. FG should not hit any of the same points. So in particular, if we have that, if we can find, for example, an element of exists x and fin k such that fx is equal to gx, then we should get a contradiction. F and G are supposed to be embeddings, again by the by one of the worksheets. I think it was worksheet 7. And this embedding, you know that basically it ought to be injective. It's again one of the properties that injectivity, the way that again we formulated with untruncated sigmas, follows from definition of embedding. And basically this grants us that the functions should at some point coincide. So as f and g are embeddings. So basically the point is, if you have an embedding from the finite set on k elements into itself, then it ought to be an equivalence. So this is something that you can prove. So as f and g are embeddings, in particular, f is an equivalence. These cross at some point. And this gets done with our lemma, right? So we've proven that this term here is indeed empty. So the entire thing is equivalent to the unit. And we've proven that these things are both units after proving the lemma. We know that this entire thing is equivalent to call product on 3 units, or in particular, the finite set on 3 elements. So that's exactly it. Okay. So are there any questions the way that we've done this problem? Okay, if not, I'll be moving to part B. So part B is generally quite, quite nice. It's done by nice induction. So we claim. So we're trying to look at the finite set on n+1 elements and choosing one out of them. Okay, so intuitively, the way it should be is that this is going to be equivalent to set on n+1 elements. So this is exactly our claim. So proceed by induction on n. So what do we have first? We have for n being 0, that we have thin set on 1 element, so, and the unit here, which we already know by the lemma we've proven before that this is just going to be a unit, which is of course equivalent to the thin set on 1 element by lemma above. Okay, nice. So now inductive case. Where n is some k+1. So okay, so we have finite set on k+1 elements and the unit here. So apply the lemma I've mentioned previously from Egbert's book, and we get that this is the choice of finite set of, well, okay, so I made a typo here where it assumed, so this is n plus k+2. And this is going to be equivalent to a coproduct of 2 choice functions. So this is going to be from k+1 to 0. This is going to be, let's say, on k+1, choose 1. So of course, the first part is going to be equivalent to 1. There is only one way to choose out of any type, the antitype. And the second part is going to be equivalent by the inductive hypothesis, finite set on n+1 elements. So this all is equivalent to set of n+2 elements by definition. This we can make definition here, and we are done. So this was a very straightforward application of the lemma. And in the first case, it could be solved by using the same lemma I've mentioned before, or we could have used the lemma we did here in class. Okay. And of course, problem C is that we claim that for any n, the finite set of n elements, from that choosing the finite set of n+1 plus 1 elements is empty. But we have already shown this by analysis on embeddings. Okay. So and with this, we're done with problem. No, what was the no in the chat a reference to? Sorry, I think I missed it. I guess it was about whether there were questions earlier. Okay, nice. All right, so yeah, so that gets done with problem 1. So it was basically just reestablishing a bunch of combinatorial properties that you're already familiar with. So now we come into the fun part of things. Okay. So problem 2 has to do with isolated points. In a way that is sort of thing more or less should be intuitive. So if we can really nicely embed the unit into that point. So, okay. So let A be a type. So definition is isolated function from A to universe U, which takes A and maps it to is decidable constant embedding of A 1 to A. So it takes an element of a type of an arbitrary type A, and it gives you this is not how I should have written it, and gives you the proof that is decidable. The way that I should written it is decidable, is isolated A, is decidable, A const A. Okay. So now we want to construct an equivalence of choosing one from A. And basically, so basically the intuition is very combinatorial, right? So we have this notion of isolated points, which are, you know, in terms of our intuitions, really are isolated points of our topological spaces. And the choice function is supposed to be counting specific things. So here we're asking to count how many sort of unit types can we spot in A, and this should correspond to sort of the isolated points we can find. So I want to construct an equivalence like this is isolated A. Okay, so construct construct a function going to the other side. So it's f going from sigma A and A is isolated A to So just unfolding the definition. So from the universe sigma, sigmaing over the types merely equivalent to 1, and X, decidable embedding into A. Just in case, recall that decidable embeddings are those embeddings whose fibers are decidable. Okay. And so we define them by when we apply F by induction on the element of the sigma type. So we have an element A of A, and then we have a proof sigma that our constant function at A from 1 is indeed decidable. This we will term as, so first we need an element of the type of things equivalent to 1. Well, we have such an element. This is 1. And of course, we can just truncate the fact the equality is an equivalence. Okay. And then we need the decidability of the embedding. And embedding and the fact that it's decidable. So here, by the use of notation, I'm going to just here say that it's const at A. So this is so sigma is both a is decidable / is embedding const A at A. Okay. So I forgot the fact that isolation at A means that the function is both an embedding and decidable. Yeah, so so the question in chat is, recall the definition of const A from unit to A is going to be defined by induction, sending the unique point to A. So this is just picking out whichever element in the codomain you have picked. All right. Okay, so let me put it somewhere here just in case. Okay. Then I'll move the definition here. Okay. So so we have our function, which is const A from the unit type to A. And now we need to prove that it's decidable, where we already have a sigma happening right here, which allows us to define it so. Okay, nice. What else? So we've constructed a function claim. It is an equivalence. And so how do we check that it's equivalence? Well, check the fibers. For example. So that's one of the ways. Another way that we can probably do that is by using functional extensionality alongside univalence, but let's do it on the fibers instead. So it's always nice to sort of, we've already established all these equivalences of different characterization of what it means to be equivalent as types. And it's good to sort of go back and forth between those proofs and maybe sort of independently just construct those two and see maybe if these are exactly the ones that get constructed out of our equivalence before. And I urge you to do that. So it's up to you, however you want to check it. Okay. So for contractability, we let x beta be in UL. So I should say, let X be in U of unit, and F sigma in our type citable functions into A. So first, we show inhabitedness of fibers. Okay, so we know that X is aligned to 1. So, and we map into a prop. So assume X is really equivalent to the unit, that we actually have a term of this type, or by univalence, that X is actually the unit type. So by functional extensionality, F is actually equal to some constant of F applied at the point. So by induction by functional extensionality, we need to check equality pointwise. So it's going to be F is going to be determined by whatever F sends the point, and so this is quite an easy equality to show. So this gives us our inhabitant. Okay, so now note that is isolated A is a proposition being a product of propositions, and so basically, what do we want to show? We want to show that the fibers are going to be contractible. Let me think about it. So we need that the fibers, we show the houses, inhabitedness fibers are a proposition. And so it's a fiber over what? Fiber over X and F sigma. Okay. Of this function. So this function sends any of those elements to these constant functions. So by functional extensionality, if we have two elements in the fiber, some A1 sigma 1 and A2 sigma 2, A1 is equal to A2, and as is isolated A is a proposition. For any A, we also get that transporting, so let this be P, transporting sigma 1 by P is the same as sigma 2. Okay, so, and with this, we've shown that it's an equivalence by showing contractibility of fibers. Any questions at this point? This was a bit kind of technical in terms of type checking because there are so many terms lying around, but the idea should be more or less understandable. Right? And I think this is really cool. So this is sort of exactly, it's a very nice correspondence of our topological methods of sort of counting and the combinatorial ones. It's if you're looking for another confirmation that the concept of the choice function is a correct one, this is one of them. Okay, so we'll then be moving on to part B. Oh, okay. So let A be a set. We claim that basically we are claiming that the choice function acts as like in the most evident way possible. So when we choose one from A, we're actually going to get back the same type that we started with. So in the proof of this is by previous part, one is going to be equivalent to sigma A and A and is isolated A. So suffices to show that all points of A are actually isolated, that for all A and A is isolated A. Okay, and after that, we're all done. So fix A and A, take A prime at A and consider the fiber sigma A x and 1 constant AX equals A. So simply considering what this type is, and by induction on the unit type and by the identity type variable, this is just going to be equivalent to A equals A prime. So right, so checking something in the fiber, like whether a constant function mapping to A applied to X is going to be the same element, is the same as checking that those two elements are the same, since again we're just using a constant function. Okay, note this is decidable as A is a set. So this type is decidable. So this type is decidable, i.e. The fiber at A. Okay. So this is one of the good things about being a set, is that our qualities are decidable. So again, so as is isolated is a proposition. We get that, what do we get? We get, so a nice way of sort of spelling this out is that this equivalence that we have established previously is going to be equivalent to exit a unit, which is going to be the same as A. So this is another way of showing this works. Since again, now we know that this element is going to be populated. So, you know, when we take an x, we apply our function above to it, and we actually get an element of the statement that A is isolated. Since it's a proposition, it's also contractible. And all is well. Okay. Any questions at this point? So another part of it, so we're gonna kind of be sidestepping part C of the problem, and we're doing part D. Let A and B be types. We claim the following equivalence. Yes, there should be an X in the sigma. Oh, yes, sorry. That did not type check originally. Yeah, everything else, I think. So here, there should also be an X. Everything else, I think is okay. Okay, nice. Thank you for spotting that. It's very important to be wary of all the type checking. Okay, so what do we have? So we have A and B types, and we claim that actually we have this following equivalence. So looking at types merely equivalent to B, types equivalent Y, X plus Y is gonna be equivalent to A. So this is also quite a nice sort of partition characterizations of choices. And this again captures like a very nice intuition about counting things. And it's about how many sort of partitions can you make when you actually have any other types, when sort of the rest of the partition, right? So what we're saying sort of is that from A choose B sort of means you can fit B in A with another type, making up A. So this is an intuition we certainly get in counting, and this is also something that we can formalize in this sort of way in homotopy type theory. So okay, so this should have this parsing. Okay, so we construct function f sort of from our double sigma y u x plus y equivalent to a. This is going to go into our type, which I'm going to, again, unfold. So types want to be that decidably embed into A. So let x be the type merely equivalent to B, y and u, and we have an equivalence x plus y to A. So f, I mean, I don't want to be abusing notation, right? Because being an equivalence includes so much information usually. So instead, I'm just going to explicitly sort of specify the element that we're going to get. So so suffices to find first an element of a type merely of types merely equivalent to B, and we have that. We have x by assumption here, which belongs in that type, and an embedding from x into A such that it is decidable. So we have such an embedding in the following way. So we have x, which embeds via left inclusion into the coproduct of x and y. And we also have an equivalence here, E. So their composition is going to be indeed our needed function. So equivalences are embeddings, and embeddings compose. So our phi, I write that down nicely. So phi is indeed going to be an embedding. Okay, so now need to show that it is inhabited. It is decidable. So this is a nice case where you really might need univalence to help you out. So take A in A, consider the fiber of phi at A, and or its negation. So we want to have an element of this. And one way you might think about it is that, well, we don't have enough information about A, but we have an equivalence with x plus y. So why not take the quasi-inverse to the coproduct and then induct on it? But you cannot induct on terms on which you've already applied functions to. This is not something that you can take from the rules of type theory. So instead, you are left with nothing. You cannot induct with anything unless you say that by univalence, x plus y is A. So instead, consider for A in x plus y fiber of phi at A or not fiber of phi at A, right? So, and now we can induct, this is a generalized variable, everything is good. So now we can induct on x plus y, I should say on A. So in the case where A is in left A, we get evidently an element. So remember now phi is going to be equal to just the left inclusion. So we get an element of the fiber of phi at A. So which the element that is going to be mapped to in left x, I should say here, is going to be x itself. Okay, and if A is in right y for line y, then get an element of the negation phi at y. How well we have the discrepancy of constructors. So two constructors of the same inductive type cannot be the same. This is something very fundamental to sort of our construction of inductive types. So if you are trying to get something, so assuming you get something in the fiber of phi, where, well, I have been not doing well on type checking. So this is going to be in left x, and this is going to be in right y. So right, so if you check something in those fibers and you're trying to get something from x, then you're going to get an actual contradiction. Okay, and so applying the in left and in right constructors, we are done. Okay, so this indeed, so originally what we wanted to show is that there is a decidable embedding, and we indeed have gotten it. So, and something that I'm gonna, what, there was a question in the chat. Okay, nice. I'm glad that it helped. Okay, so this is really the power of univalence. Some things really, because type theoretic rules are sometimes too unforgiving for substitutions and ungeneralized elements, univalence sort of paves a way to do a lot more induction. Okay. And so something to check. This is actually an equivalence. So the way we can do it is by constructing a quasi-inverse, right, from now our type, which is again going to be terms which are merely equivalent to B, and those go decidedly into A. And this is going to be XYB, YY, X plus Y is equivalent to A. However, this might make it a bit hard because, as you can see, there's not a lot of information about what the type that you don't hit looks like. So something that you might think about is maybe using law of excluded middle, but that's not something you want to show. So instead, try to use contractability of fibers. Right. So is there, I'm just thinking, so it's a good idea to sort of work by yourself on this, but I'm also trying to to think about what is happening. So I think this surely is an embedding, and maybe it would be enough to show that it's merely surjective. But yeah, so one of these cases should be working very nicely for this sort of problem. So another thing that we will now be looking at are type of unordered pairs. So let A be a type. We define type unordered pairs A to be this type. So there's a way you can think about doing this by just supplying some relation maybe on them. But instead we can also say that, well, let X be a something that's merely equivalent to a finite type on two elements. And so we can sort of like choose 2 points, right, in A, possibly the same. So this is the intuition behind this definition. And now we, of course, want to have sort of an evident result. So we construct an embedding. Okay. Embedding of Booleans in A. And then into unordered pairs A. So this is important. These are sort of 2 different ways of counting, right? So this is not asking for the function sort of for the 2 elements that we pick to be picked nicely. Here we're actually asking for isolated points in some sense, right? So that bool is actually a coproduct of 2 units. So in some sense, we're asking to pick 2 isolated points. This is not generally what the unordered pairs selection does. So we ought to see some sort of difference behind them. So we first construct an embedding and then actually show that these 2 types are there's something that the embedding does not hit usually. So first, so construction, I should say. The construction goes in sort of the usual way. So again, so this is some X in universe of Booleans such that X decidedly embeds into A. And this is, of course, our original type. So instead, we can use now univalence to say that BS2 is the same as bool. So this goes by univalence. And the fact that the bool, as you usually define it, an inductive type on 2 elements, is actually going to be equivalent to a coproduct of 2 units, which is actually going to be equivalent to the type of finite sets on 2 elements. Okay. And so the construction is a forgetful one. what do I mean by this? Well, here we have functions of, so here we have a sigma type. It takes something that is that is like a Boolean, that is merely like a Boolean, and gives you a decidable embedding into A. And so we simply forget the fact that it's a decidable embedding and take that function as the element in our codomain. So this is what I mean by forgetful. The only thing that sort of we're doing is saying that there is this extra information which we're not going to be using in the construction of our function, and we simply forget that it exists. Okay, so note, what's the easiest example we can think of something that will not be hit on in the codomain? So note, not all functions need to be embeddings. Decidability is this, it's personally, I think it's a hard property to get a grip on sort of intuitively. Without establishing a lot of properties beforehand, I wouldn't know like what sort of things and fibers are decidable or not. And so instead we can look at the following facts. So let A be defined as bool, and define so the usual truth function from bool to bool, which sends everything to true. This is surely not an embedding. This is surely not an embedding. So surely true is equal to false, which is equivalent to the empty type. Imagine that we're trying to construct an embedding, but that is not possible, and it is not trivial to tell that it's not possible. How could we realize that it is not possible to construct this embedding, and how could we prove that that is not possible? Well, I mean, the way it's what would we tell somebody at like a mathematical logic intro class? Depending on your statement, take its negation. So if you have universal quantification here, so for example, here we're talking about quantifying over A being a type, then we need to actually construct and provide an example of a type for which there will not be such an embedding. So in particular here, where we've picked a type A, right? We've defined it as bool here, and I've provided you with a function that I'm telling you is not equivalent, right? Yeah. So it's it's basically, I mean, the way that you do it inside type theoretically, if there's of course informal mathematics happening on the, we can talk about doing things informally, or we can do things formally. So I mean, right, the usual way, if you can formalize A, you can also formalize the negation of A, which is exactly what it would mean to prove that there is no such thing. Like you can formalize the fact that, I don't know, if you're trying to make an existence claim, just an existence claim, a plain one, you can say that let me use already an notation example. There does not exist, right, f from, I don't know, from A to X after you fixed X. Since we have univalence, maybe it's all right here to take bool. Yeah, so there does not exist. So so there merely exists, for example, A in the universe such that there do not exist merely a function from A to bool such that is embedding F holds. So something like this. So it's always a matter of just formalizing things and, you know, just negating whatever statement you need to negate. Okay. So yeah. So this is a nice example of how there are two different ways of counting. And we should not confuse those. Okay. So we're slowly running out of time. The rest of the problems that I'm not going to cover will be, as I mentioned, covered in the North American problem session seminar. So let's go with problem 4 now. And just finish up with these nice, clean proof. So claim taking two elements out of finite set of n elements is the same as sort of summing over finite sets of k elements here. Okay, so this is you know, quite straightforward, should be. So proof by induction on n. So when n is 0, what do we have? So this is just fin 0 bool, which is going to be equivalent to, of course, just what this is going to be the definition. It's going to be choosing bool from the empty type, which is, of course, by the lemma you can see in Egbert's book, this is the same as the empty type, which of course is the same as sigmaing over the empty type for anything. Okay, which is, of course, definitionally the same as taking k in fin set. Okay. This should be 0. Okay, nice. Yeah, I'm gonna say that English is not my mother tongue, so I can be excused from making such silly claims and neologisms. Okay. Right. Nice. So what else do we have? So now so now the inductive case is when n is k plus 1. Okay, what do we have then? So we have fin k plus 1 bool. So okay, so this is equivalent, of course, to fin k plus 1. So this is definitionally, and bool is going to be equivalent to a coproduct of 2 units. By lemma, in Egbert's book, which we've used before, this is going to be the same as choosing a unit from finite set of k elements, and then taking a coproduct of finite set on k elements, choose 1 plus 1. Okay. So we've proven in a lemma before the finite set on k elements is indeed a set. So, and by the lemma before, it was one of the problems we did previously. Yes, this problem B. So if A is a set, then we have this following equivalence. So we just recover the set itself when we choose this point. So this is going to be just finite set on K elements. And this, by the inductive hypothesis, is going to be, let me write it in a different color. So plus, and this by inductive hypothesis will be just the sum over elements in, well, I should now choose another letter M on fin K elements, fin M. So maybe I should make this like blue. So this is by inductive hypothesis, and this is by one of the problems. Okay, nice. And something, so I should be wrapping up. So I should say claim. Sorry, this is a clear one. So when we take this sigma K lots of M element, that this is exactly going to be, this is basically like counting. This is going to be exactly the set of M in fine K plus 1 fin M. Okay, which indeed proves then our claim. So yeah, so these are some nice counting arguments which we've seen, some sort of notes on how what it means to be sort of isolated, how these how there are different ways of counting, and whether these can be compared, and sort of getting topological intuition out of it. So hopefully that helped. Are there any questions before we end the session? Okay, so it seems that everything's fine. So I wanted to say, oh, infinite combinatorics. So what exactly do you mean by that? Right, so Ramsey theory for infinite. So yeah, so you can indeed specify a bunch of, I mean, so there are of course a lot of technicalities to go into, but this is how I would answer your question. So homotopy type theory is supposed to serve as a foundation of mathematics. In this way, you should be able to encode everything into it, including the definition of like what it means to be a set. Like we have some things called sets, and you can talk about establishing, you know, the notion of their size via the notion of, you know, there being bijective functions between things. And henceforth, you can also establish, you know, you can, for example, talk about the cardinality. You can talk about omega. You can talk about Aleph null, that is, by talking about sets which are in bijection with the type of natural numbers, right? So for everything else, it becomes a bit harder. I would say because sets are a little bit more structural than in material set theory, in homotopy type theory. And that is something that I urge you to, for example, ask in the Discord chat, for maybe Egbert might see. So he's the one who's been actively developing Univalent combinatorics, and it's been doing a lot in the finite case. I'm not sure what happens in the infinitary one, and whether as we can actually have something which resembles really closely usual combinatorics would do with set theory. Yeah, so I urge you to do it. It's a very novel, it's a very novel thing. Nobody really did combinatorics with all these things inside HoTT before Egbert. So yeah. Okay, so I guess yeah. I guess we'll be ending this problem session. Thank you so much for sticking around. Thank you so much for listening to all the stuff at the HoTTEST summer school. Hopefully we'll see you around. And again, if you wanted to hear the solutions to, for example, problem 5, I urge you to go to the North American session on the YouTube channel and watch that as well. Okay, thank you.